Hello everyone. So today we're going to go over section 3.11, related rates. Suppose we're given a function y equals f of x, and both x and y are changing with respect to the variable t, then we can find the related rates dx dt or dy dt, and that is how fast x or y are changing with respect to some variable t, usually stands for time. Now, solving these related rates problems often requires the use of implicit differentiation. So if you look on the right here, we're given an example in terms of the area of a square. Area is equal to x squared, and suppose x is changing with respect to some t time variable. Okay, so we can label this diagram here. The sides are x. The area is, of course, then x squared. And as you can see here in red, the lengths x are increasing, so, and therefore the area will also increase. Okay, and it's related like this. We have a equals x squared. If we take the derivative of both sides, we have dA dt, which is the rate of increase or decrease of the area of the square in terms of time. And that's going to be equal to 2x multiplied by dx dt, and that is the rate at which the side length is increasing. dA dt and dx dt are related rates. Okay. So another example of this would be the falling ladder. So suppose the ladder is propped up against the wall. So is some distance x away, the base of the ladder is some distance x away from the corner, and the height is y, as in the ladder reaches a certain height of y. The ladder is of fixed length, we'll call it L. So the relationship between the three sides is, of course, x squared plus y squared equals L squared. Okay, we'll work with an example involving that diagram in just a bit. But for related rates problems, we have some general steps to follow. We're going to draw a diagram if possible and write down the information using the appropriate notation. We're going to write down the rate that we're generally solving for and the rate that's sometimes given. And then we're going to write a equation that relates the variables together. And then if we differentiate them, we can find the related rates. And then sometimes we have to also, before doing that, use some matter of substitution or some geometric properties to eliminate some of the variables or simplify them. And then we're finally going to substitute the information into the resulting equation with the related rates and find the unknown rate. So let's see how that works in practice. See here we have a spherical balloon. Volume increases at the rate of 100 cubic centimeters per second. How fast is the radius increasing when the diameter is 50 centimeters? So for this question, you can see first that if the diameter is 50, then the radius is 25 centimeters. Okay. And that is this length right here will be 25, will be 25 centimeters. At the time for which we want to find the rate of increase of the radius. So that is to say, we don't know what dr dt is at that moment. We do know what d phi dt is. That is given to us. And that would be 100 cubic centimeters per second. Okay, so the relationship between the radius and the volume of a sphere is, of course, v is equal to 4/3 pi r cubed. So we can take the derivative of both sides. dv dt is equal to 4/3 pi and then 3r squared dr dt. In this case, we know what dv dt is, so we can substitute 100 4/3 pi. And then we know we're looking for the rate of increase of the radius when the radius itself is 25, so we can substitute r as 25 here. Okay. Then by doing some multiplication, you can find 25 squared is 625, and then times 4 is 2500, so we'll have 100 is equal to 2500 pi dr dt. Of course, the 3's will eliminate each other, so let's just indicate that as well. They are. And then simplify there. So once we solve for dr dt, and that is the rate of change of the radius in terms of time, we'll get 1 over 25 pi. And then the units for this would be centimeters per second. Okay. So as you can see here, we started by labeling our diagram on the left. We related to the two variables in question, and then we use implicit differentiation, substituting with the values, and then finally we found the rate. So that's going to be the pattern for the rest of these examples here. Let's look at example 2. This is the falling ladder example. Okay, a 10-foot long ladder rests against a vertical wall. If the bottom of the ladder slides away from the wall at the rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so again, just like before, we're going to label this diagram. We have x, the horizontal distance, y, the vertical distance, and the length of the ladder, which is 10. So in this case, the bottom of the ladder is sliding away, the top of the ladder is sliding down, and we know that the rate at which the ladder is sliding away from the base of the wall is 1 foot per second. We're looking for the rate at which the top of the ladder is falling. And we know the relationship between these two variables is that x squared plus y squared equals to 10 squared. Okay, so we can take the derivative of both sides. We'll have 2x dx dt plus 2y dy dt. And that's going to be equal to 0 on the right-hand side. Okay, so we are looking for dy dt, and we can isolate the variable, but it might be easier just to substitute in values because we already know what some of them are. We know that x, for example, we're looking for the rate of change for the dy dt when x is equal to 6. And that is when the bottom of the ladder is 6 feet away from the wall. So we can substitute in 6 here. We already know that dx dt is 1. And then we have 2. Now, for the y value, when x is equal to 6, what is y equal to? We can actually find that using the relationship between x and y. We know that x squared plus y squared equals to 10 squared. So if we substitute in 6 for x, we can find out what y is at that point in time. So this would be 36 plus y squared equals to 100, which of course means that y is equal to y squared is equal to 64, and y is equal to plus or minus 8. But for us, it will be plus 8 because the ladder is up 8 meters from the corner. Oh, sorry, 8 feet. All right, so we can substitute an 8 here. So we are just left with dy dt as the sole unknown. And then you will get, let's see here, so negative 12 is equal to 16 dy dt. And then, so finally, if you divide both sides by 16 dy dt, and that is the rate of change at which the top of the ladder is falling towards the ground, will be negative 3/4 feet per second, which makes sense. It should be negative because if we make the assumption that up 8 feet is the positive direction, and then we know that the distance is decreasing, so it makes sense for it to be negative there. All right, let's look at the next example together. This one's a little bit more involved. Okay. So pouring water into a cone. A water tank has the shape of a inverted circular cone as drawn on the left here. The base radius is 2 meters. Okay, so let's label the diagram as we find out this information. 2 meters here, and the maximum height is 4 meters, so this would be 4 meters. I'm gonna write to the side. And the water is being poured in the tank at 2 meters cube per second, so this would be dv dt. Actually, I'm gonna write it to the other side. dv dt is equal to 2. Find the rate at which the water level is rising when the water is 3 meters deep. So this would be 3 meters deep here. So again, we want to relate all the variables together using a equation of some kind. In this case, we have v is equal to 1/3 pi r square h. Okay. Now notice that we have a variable r here that we wouldn't know what to do with because we're looking for dh dt. Right, we're looking for the rate at which the water level rises. If we take the derivative of the current expression, we'll have some kind of dr dt and some kind of variable r, which we wouldn't know what to do with. So we have to find something to relate the two of the variables to each other. So in this case, if you look at the diagram, oops, even blue. Okay, so this is 2 meters here at the maximum. The whole entire cone. This is a cross section of the cone on just the triangular side, as you can see here. Same thing. So this would be 4 meters. All right, and the idea here is, suppose I mark the 3 meter mark somewhere here. Whatever this triangle is will be a similar triangle. So this would be H and R. And of course, these two triangles are similar. The one that's 4 meters and 2 meters, and the ones that is marked with R and H. So because they're similar triangles, we know that R divided by H is equal to 2 divided by 4. The ratios of the sides of these similar triangles must be the same. So we can solve for R. R is going to be equal to H over 2. And we can substitute that into our equation here on the left. So we have V is equal to 1/3 pi, and then H over 2 squared times H. Multiply everything out. That will be, let's see, pi over 12 and H cubed. From there, you can take the derivative of both sides and use implicit differentiation. So that will give us, let's see here, dv dt is equal to 3 pi over 12 and then h squared times dh dt. All right, dv dt, of course, is 2. at the moment, we know that, oh, actually, we can simplify this. This would just be pi over 4. H at that time is 3. So we have 3 squared, and then dH dt. So really, this would be 8 over 9 pi will be equal to dH dt then. Oh, actually should include the units here. That will be meters per minute is equal to dH dt. Okay, so the challenge of this question is recognizing that we have similar triangles and being able to work with them. It's a little bit of additional geometry that you have to do, which is interesting. All right, last question, or last example. A man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet away from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So, let's see here. 15 feet. The rate at which the man walks, so dx dt is 4 feet per second. We're looking for this rotation, which is, of course, d theta dt. Okay, and over here on the left, so draw the diagram again. Just make sure that everything is nice labeled. We have 20 x and theta. Of course, how to relate the two variable is that tangent theta is equal to opposite, which is x, over the adjacent side, which is 20 feet. Okay, now we can take the derivative of both sides using implicit differentiation. We have secant square theta is equal to, oh, sorry, secant square theta d theta dt, of course, is equal to 1 over 20 and then dx dt. Now, in order to finish this question, we have to find out what theta is when x is equal to 15. So when x equal to 15, this is 20. We have to find a theta in that moment in time. So that would be tan theta is equal to 15 over 20. So theta is equal to arctangent 3/4. So we can substitute that into our expression here that we're working with, and that will be secant squared arctangent of 3/4. That's the angle. D theta dt, the rate that we're looking for, is equal to 1 over 20. And then dx dt at that moment is, well, 4. Okay. So that means, if we continue here, that d theta dt is equal to 1/5 cosine squared, and then arctangent 3/4. It's going to go ahead and use calculator for that part, and you'll get approximately 0.128 radians per second. All right. So those are the different kinds of related rates question that you might encounter. And that's it for today. So thank you for listening.